Guys, pressure drop in a packed bed reactor, how to deal with the Ergun equation. This is all the second part of the video. In the first part, I feel like I didn't do a great job explaining. I mean, I kind of introduced it, worked the equations and all that. But let's review real quick, okay? So this part right here in the blue, I'm going to make it black, is the equation that we worked to. We basically acknowledged the fact that the concentration over here can be explained through the expansion factor. Again, I have a video on that. Also, down here is basically Ca plugged into a material balance, right? Basically this equation, the concentration, you plugged it in, and then we got that long equation. And the third part, the takeaway from that video, was that we had dx dw as a function of conversion and pressure. Okay, so to solve dx dw and get an equation, this comes from differential equations class, but we're going to need, we can solve that with, oh, I'm sorry, my marker isn't working. What the heck? No, come on. There we go. dp dw. We need an equation dp dw as a function of, it could be conversion of pressure or weight, any of those. Okay, so we could solve that if we'd have an equation of dp dw. So that's the goal of this video, dp dw. So how do we get that from this equation? We have dp dz. Well, it's pretty close. Change dz to dw. So this whole part of this video is going to be about how to do that. Okay, let's get started. So this is the Ergun equation. Okay? And basically what it's saying as a review, so you got a pipe like this, and this is your axial direction. I'm going to call that the z direction. Okay? So as we traverse this way, there's going to be a change in pressure. As we change z, we change p. Okay? So let me go through each variable and tell you what it means, because what we got to do is identify which variable in that equation is not constant with a change in z. Because if pressure is changing with a change in z, you know there's got to be some parameter on the right side of the equation that's changing with z to make this equation even make sense. So the superficial mass velocity, let's start there. Okay, so this is the less intuitive one. So superficial mass velocity is going to give you kilograms, right, per a unit area per second. So it's basically saying, well, if I took a unit area here, there's a mass flux through that unit area per second. So let's move in the z direction. Let's make a second one. Let's say you have this. Now I know what you might be thinking. Well, hey Brian, the gas density is changing coming through here, right? Because we're changing the number of moles. That's all why we're doing this. Well, if you have the flux going through here, let me do a different color. Let me do the magical blue. I love this color. There we go. Coming through here and coming through here, the velocities of the gases are different. What the heck? So wouldn't the g be variable? Well, the answer is no. Because you have, let's call this location 1, this one location 2. So the mass balance, say P1, right, the density, times the volumetric flow, Q1, both are different than P2, Q2, but together they're the same because you have a conservation of mass. So if your density got higher, or you had more of this, right, your volume would go down to compensate to make it equal to this. The mass going through those two squares are the same. Okay, so G is constant. The void fraction, well, if the packing's consistent throughout the whole column or the whole pipe, that's going to be the same. Viscosity will be the same. Temperature's not changing, right? We determined that's constant. This is a constant diameter of particles. Hopefully the constant can vary a little bit, but the packing is the same packing throughout. Your gravitational is constant, but your density is not. I mean, according to this, we got there. So that's the variable. The density is what's changing. Okay? So let's take that into our own hands here. So we're going to say P1 times Q1 is equal to P2 times Q2. I use Q because V looks like velocity. Okay, so we want to know if this is, we're not going to say P1, we're going to say P initial and P sometime later, and Q initial, that's Q sometime later. So let's solve for that P that we got in there. Well, what we got is P naught, Q naught over Q, and we've already determined in previous videos we can use expansion factor to explain Q. So Q naught is going to be 1 plus e to dx, right? And over here we're going to put P naught over P, T over T naught. Okay, and plug that in for Q. This is a expansion factor video I did. Okay, so P is equal to P naught, Q naught over Q naught, 1 plus e to x, just subbing the other equation in. This will be P over P naught, inverted basically since it was in the denominator. Sorry, T naught over T. I had a lot of coffee. Waiting for that to wear off. Okay, so that's our density. So we plug this into the Ergun equation, right? So I'm going to copy this. Let's copy that and bring it down. It's a really long equation, very hard to remember. Okay, so basically you got dp dz is equal to negative g rho, not rho, but we're going to plug everything in. So I'm going to plug in rho naughts. The q naughts will cancel. I'm not going to put the 1 plus ex, at least in this first part. I'm just going to fill it in with gc dp from this side, rho naught in there, g. 1 minus the void fraction over the void fraction cubed. I'm setting it up so it's nice and neat. I'm going to write everything that's left over here to the right side over here, basically. That's what I'm aiming. Okay, so viscosity dp plus 1.75 g. Let's open up some more room. Okay, now I'm going to put in what's left over. So we got in red here, here, here. Okay, so let's put that in. So since we had p on the denominator, the 1 plus e to x comes up here, the expansion factor part. P naught over p, t over t naught. Okay, so that's what we got. So this is the new Ergun equation based on the plug-in for density, acknowledging that density is not constant. So we account for that with this plug-in. Okay, next step. What do we do? All right, so the next step is to handle your dz. Make that dw. Okay, so dz, let's take w. What is the weight of the packing? Well, I'm going to draw over here so we can get a better look at it. So let me ask you something. Can I use the void fraction to describe this? Yes. So let's take z. Z this way, the cross-sectional area, that'll give you the volume. Z times the cross-sectional area will give you the volume. Okay? Now the next thing. The density of the catalyst will give you the mass of the catalyst. But remember that all the packing inside here, there's an empty volume. Not all of it's packing. It's not 100% packing in that volume. So not the void fraction. Void fraction gives you the empty space, but 1 minus the void fraction will give you the volume of actual packing. So now there you got it. Now you got all of this together. You got the volume times the density, which give you from here to here you got the mass. From here to here you got the actual mass. This part right here is the actual mass if the whole thing was filled with packing, no empty space. This accounts for the empty space. So basically throughout that calculation you get the mass of the actual packing. So let's take dw in terms of dz, right? So then you get AC rho c 1 minus theta, and your z drops out, taking just a basic derivative. Then we want dz in terms of dw, so then what we're going to do is we're going to move dz to the other side, and we're going to have dw, with all this divided over 1 minus theta. So that's our plug-in for dz. Okay, I'll see you guys in the next video. I'm going to plug that in and continue the analysis. I might be running out of time here.